Okay, lecture 3, change of concentration with time. Now, we're going to deal with a first order reaction in this first problem. And the rate law that we knew, or we know already, a general one for the first order reaction is this. Well, if we integrate across concentration and time, we end up with this form. This is the integrated rate law. And they derive it in the book. The derivation isn't part of any exam, so all you need to know is this. But check out the derivation if you like. If you had some calculus, you should be fine. But notice we have a relationship between the initial concentration, the final concentration, the rate constant, and time. So if we know what we start with, and we know K, and we can determine what concentration of the reactant is left over after a certain time. If we know if we know what we started with, we know what we ended with in concentration, and we know K, we can find how long it took. So it's the relationship between concentration and time. Very useful when we're in a practical lab setting. So first order reaction has a rate constant of 0.0250 inverted seconds. That's your K. Initial concentration, and then they have the time. So what is the concentration? What is the final concentration after 1.5 minutes? So if we put this into the equation, they say they want to know the final concentration. That's what this term is. We don't know it. The initial concentration is 3.00 molar. K, the rate constant, is 0.0. So you need to be able to pick out each term in these equations, or in these descriptions of the problem. And then the time is 1.5 minutes, or 1.5 minutes. And see, this is inverted seconds. So this has to be, we convert to 90 seconds. So 1.5 minutes is 90 seconds. We're almost always going to have to convert to seconds because the rate constant is almost always given in inverted seconds. Now see, we have seconds and inverted seconds. They cancel, and they have to. Anytime we have a logarithm, its argument, the thing that the logarithm operates on, has to have no units of measure, and it has to give back a number. Well, we have molars here. Moles per liter are called molars. Molars here, this would have molars, so those will cancel. It's just a number. And the natural log of a number is just going to be another number. So all of the units have to cancel. So keep that in mind. That will help you out as well. Carry the units through. And we end up with, this is minus, and so this is natural log of the concentration of A over 3.00 molar. And what we do then is e to the natural log of x is x. So if we have a natural log, if these were two numbers, we just take the numbers and take the natural log, but we have a variable in here. We have to get rid of the natural log. You can't just cancel natural logs. We have to operate on each side, so we have e to the natural log of x gives us x. And what we're doing, e to the x is the anti-log. This is something straight out of your math course that you should have taken before this class, so I'm only going to cover it briefly, but what you do is take e raised to this side of the equation, and e raised, or this side of the equation, e raised to this side of the equation. So it's just putting e's on either side. Really what we're doing is take the anti-log of both sides. If this is just startling, then you want to let me know, because this is algebra that you should know. Nothing new here as far as if you've taken the proper math courses. If you haven't, that's fine. You just got to let me know, and you have some work to do. So we figure out, we rearrange. This is 0.105 times 3 molar, so this gives us 0.315 molar as our answer. Now, a couple of things. We need that negative in here, way up here, because this term is always going to be less than the starting concentration because it's a reactant. It should drop away with time. Since this ratio then is going to be less than 1, the natural log of it is going to be negative. So the negatives will cancel. In this case, we don't see it. It kind of gets washed away in the rest of the calculation. We'll see it in another calculation, but we need that negative in there. And when we determine the final concentration, it has to be less than what we started with. We started with 3 molar. This is 0.315 molar. So that's good. It doesn't mean that we're right, but we're definitely in the ballpark. If this came up to be 31.5 molar, we've done something wrong. So always be checking on that kind of thing. Now let's do another one here. First order reaction, and we have the rate constant. Here's our K. If the initial concentration is 2.1 molar, how long will it take for the concentration to drop to 0.555? So this time we have to find T. So I'm going to do out as many different variations as I can. Here's our equation for first order. Again, for my class, you need to know this equation. You need to have it memorized for the exam. You work with it enough, you don't really have to memorize it. You'll just beat it into your skull because you're going to be doing so many of these problems. So that's how you always want to approach this. It shouldn't be a burden to memorize these equations, because if you do 10 of these problems, you'll never forget it. The K value, notice inverted seconds here, and this time we're solving for T. Well, when we take 0.555 divided by 2.10, take the natural log, we end up with minus 1.33. Since this number is smaller than this number, this whole term is less than 1. The natural log of something less than 1 is going to give us a negative value. That's why we have that negative there, as I stated before. Now it's a little more obvious what's going on. And then when we solve for it, so these cancel, as they should, because T has to be positive. And we end up with 11.1 seconds. Again, I took this equation and converted it into this form. If you don't see it, if you don't see how I got from this point to this point, then your math skills aren't where they need to be. Doesn't mean you have to drop the course or anything, but it means you might have a little work to do. Because we're going to be doing a lot of these kinds of algebraic manipulations. You need to know how to do them. Let's try number 3 here. Moving fast, but it's because there's not too much to these problems. It's just an equation. You put in the proper values. And you can always replay it if I go a little fast. But if you get this, you should pause right here and try to solve this problem. Don't wait for me to do it if you know what's going on. Now, the initial concentration in a first order reaction, again, I always have to tell you that it's first order. Actually, from the units of K, inverted seconds always means first order. And in some exams I've seen, standardized exams, they assume that you'll know that. But I don't. I always tell you what the order of the reaction is, and you just have to be able to know what the equation is. So first order is, okay, so the initial concentration is 0.4 molar. Let's just put that in. The final concentration is 0.1 molar. So we know the whole side here. So that'll be nice here. We just take, it's going to be 0.25, take the natural log of it. Minus, so what's the rate constant? We don't know that. And then T, now they say they want the rate constant in inverted seconds. If you put T in here as 6 hours, which is given here, that's fine, but you'll just end up with inverted hours, and then you'll have to convert to inverted seconds. I don't like to do that. I make mistakes that way. I mean, if I stop to think, it's not a tough conversion. It's just an unusual one for me. And if I were doing it on the board, I'm doing this really quickly for people. More of a mistake, more of a possibility of a mistake. So always want to limit those possibilities of making mistakes. So I convert to seconds. You're free to do whatever you want to do. If you want to leave it in hours, you can. Leave it in minutes if you want. Convert it to minutes. Convert it to centuries, get inverted centuries, and go from there. But I think it's easier to do it this way. So 1.39. And note I'm going pretty fast on the math too, but this is not 1050. And I'm not going to spend a lot of time on this video showing you how to do basic calculator skills. You need to know how to do that. If you don't, and you can come to me, I'm not going to laugh at you. If you need some help with your calculator, absolutely. I can help with that, but I'm not going to do that on the video, assuming a certain level. And we have 6.44 times 10 to the minus 5 inverted seconds. Those are units for a first order reaction. Every first order reaction K is going to be in terms of inverted time, and usually inverted seconds. All right, let's try another one. What else do we have here? So a second order reaction. Now we're into second order reactions, and let me get this. All right, and let's write out the second order reaction. That's the equation. Need to know that for second order. I'll tell you what order it is, but you need to know what the corresponding equation is. This has a rate constant of 0.144. Let me write it out here. 0.144. 1 over molars times seconds. This can be written in this form. And this is what gets students too, is that could write this as 1 over capital M times S, or we could even put liters over moles seconds, and that, it's the same units. There's a lot of different ways of doing this. This happens at the higher levels. We just get so many different versions, or so many different ways of writing the same thing. Now, the initial concentration is 1.4 molar, and we have to find the final concentration. Now, that's why I carry the units through. Let's do this out. This is 8.21 inverted molars. 1 over 1.4 molar gives us 0.714 inverted molars. So same units, and we're adding them, so they have to be the same units. And then we have this. If you carry these units through, and I know you're going to get very tired of me saying you got to carry those units through, but it is so important. In lecture, I give you some examples of how it's helped me out. I guess the one that I use a lot is, now notice this 1 over the concentration is equal to 8.92. We're going to take the reciprocal of both sides, so this is going to be 1. Before I interrupted myself, oops, 1 divided by, dang it, 1.89. There we go. And this is 0.12 molar. So we're back to molars like we should be, and that's the answer. And just really quick, when I was in my physics course, I didn't have a chance to study for an exam. I walked in, and I didn't know what they wanted, but I knew the units were of energy. So I just took all of the different terms that they gave me and made sure that when I was done, all the units came together to form kilograms meters squared per second squared, and I was really surprised that I got all of the problems right. Without actually knowing exactly how to get there, I just used those units to drive me towards the answer. Now this, I want to carry those units through. It will help you. Second order again, and I'm changing this because I just noticed that you can try it, but we come up with a somewhat nonsensical answer, and what it means is that the reaction has just gone to completion, so we want to use 0.35 minutes. At least that's what it looked like to me when I did a real quick calculation beforehand. Okay, so we have K. They give us that. 0.35 minutes is 21 seconds. The initial concentration we don't know. The final concentration, they tell us, is 0.940 molar. 0.00673 times 21, and this comes up to be 0.141 inverted molars. We don't know what A is, or the A naught is, and that's the way you can say that, A naught. Initial concentration, this is 1.06 molar, inverted molars. Subtract, so 1.06 minus 0.141, and we end up with 0.919 inverted molars, 1 over A naught. Take the inverse of both sides, and the initial concentration is 1.09 molar. Sorry if I was off the page there. Our final concentration was 0.94 molar. This is 1.09 molar. It's greater, so that's good. If it had been less or it had been negative, something went wrong. So that looks good. I'm going to do a real quick double check. Oops, oh, that's nice. 0 point. Yeah. And then over here, yes, minus, take the inverse. Yep, looks good. Okay, one last problem. This is a zero order reaction. And I'm only doing one of these because, you know, I think you have a pretty good idea of how to solve these now. This is the zero order equation. You need to know it. But I'm just going to solve one because it's the same as the others. You have 4 variables to start out, and then you tag down 3 of them with particular values, and then you solve for the last one. So we have zero order reaction. You need to know that that's what this equation is, or what this equation uses, is this zero order integrated rate law. The rate constant is 1.33 times 10 to the minus 5 molars per second. Those are different units, but notice that this is molars, this is molars. So and time is seconds, so those seconds will cancel. That's the correct units for the rate constant for a zero order reaction. 2 hours, that's 7,200 seconds. And actually it's just 3 significant figures because we only had 2.00 hours, but we'll leave it like that. And then plus the initial concentration was 12 molar. And we need that negative there. Forgot that, because if we had that, it would just add on to this concentration, making the final concentration greater. Can't be. So when I looked at it really quick, I see there's something missing, that negative there. And then we have 1.33 times 10 to the minus 5 times 7,200. And we end up with minus 0.0958 molar plus 12. And then, and we end up with 11.9 molar for the final concentration. And we'll just stick with 3 significant figures. You might be able to tell that if this time went up high enough, this value would become greater than this value, and your final concentration would be negative. What that means, this is a linear equation, and it's just the equation that models everything until the reaction is done. When the reaction is completed, then this side should be, your final concentration should be 0. So if it becomes negative, it means that you just went too far. The reaction is already over. So this equation doesn't know the reaction is over. If you put the nonsensical values in, you'll get a nonsensical answer. So you also have to recognize the limitations of your equations. And that's one of them here.